Now we will begin our invited speakers session number 3. We would like to invite and introduce you Professor Dr. Branislav B. Todorovic from University of Belgrade. Yes. Professor, he will be leading this session. He is the panel's chairman, and also he is member of ESHREA and President of National Serbia Society for HVACR. Thank you.
Good morning, ladies and gentlemen. We have to start. We are already 15 minutes late, what means that each speaker has to be shorted for 5 minutes. Better to tell them so, you know, because then they will not be surprised to be longer. And I have a privilege to chair the session where our very famous 3 speakers, something like yesterday. And I will start to introduce to you Mr. Eckhard Groll, Professor of Mechanical Engineering. I know him when he was in high school, I think, but in that time he was not PhD, but now I see what he has done during his life. If I'm going too many in details, then we will be really too late. He's Professor of Mechanical Engineering, also services as the Director of the Office of Professional Practice of Purdue University. He started his career in Germany, where he was living, and he made a PhD in very famous university in Hanover. Now he is full professor in Purdue. He is teaching thermodynamics, and he has research focus on the fundamentals of thermal sciences. So we have a privilege yesterday, today, and tomorrow, including me tomorrow, to listen to very famous people who really are knowledgeable. If I will continue, then you will not have time to speak. Anyway, so please, I think that's enough. But I have to mention that you are co-author of 3 books, that you have many articles in 180 scientific journals with very high index, and continuing so, you have still time to...
Started this during my PhD days at the University of Hanover, as introduced with Professor Horst Kruse as my advisor at that point, and then when I came to Purdue, had the opportunity to continue to work on compressors. So let's see if I can move this along. This is the outline of my presentation today. I will talk to you a little bit about, I'll give you a short introduction and talk a little bit about modeling of compressors as an analysis tool that we use to evaluate the performance or do design modifications of compressors. And then I go through some examples of this type of compressor that we're analyzing. These are some novel concepts, compression concepts that we analyzed over the years, and just to give you a rough idea of how to use these analysis tools in the real application. And I will talk about these various compressors in more details as we go along. So let's start with an introduction. I differentiate compressors predominantly into positive displacement machines and dynamic machines. I'm on the positive displacement side. My whole career has been on positive displacement. If you're looking for dynamic expertise, rotating machinery, like a centrifugal compressor or an axial flow compressor, then you will have to talk to somebody else. On the positive displacement side, where I operate, we can differentiate by recips, rotaries, or orbital compressors as some type of a driving mechanism, and rotaries maybe farther to differentiate between rolling piston or rotary vane or screw compressors, just to give you a little bit of an idea. And orbiting, a typical compressor most common used is the scroll compressor. If you look at the refrigeration, air conditioning, heat pumping industry, we predominantly operate 5 types of compressors. That's recips, rolling pistons, screws, and scrolls, and then centrifugals for very large application. And so if I put these compressors on an axis for capacity. By capacity, mean cooling capacity, from very small, like a domestic refrigerator freezer, to very, very large air conditioning in large commercial buildings. Right? You see roughly an application range for these 5 dominant types of compressors. Recips maybe still have the largest application range, from very, very small fractional capacities up to 200 kilowatts with multiple machines, multiple pistons in parallel. Rotaries are much smaller applications, typically small refrigerators to residential type small scale packaged air conditioning. Scrolls are predominantly in the air conditioning and heat pumping range for residential and light commercial applications. And then screws go for the larger commercial applications and refrigeration applications. And then also the centrifugal, as I mentioned, for very, very large air conditioning. So if you look at this map, it looks like we're in pretty good shape. We have compressors for all of the sizes that we need, for all of the applications that we need. So while looking actually at some novel compressors, maybe some new ones, different driving mechanisms at work over the years that have been the reason for why I'm in business and do this type of research. Some of them is driven by new refrigerants, new working fluids due to ozone depletion or global warming, right? And yet we are looking at new working fluids again. We're moving potentially to HFO refrigerants, and some of these refrigerants do require maybe a slightly different compression mechanism or favor a different compression mechanism. Clearly, when we went to CO2, high pressure refrigerants, all of a sudden it was much more difficult to seal. And so a certain type may have advantages over another type. But there are other aspects. Sometimes it's a new application. We have looked at electronics cooling, for example, packaging a vapor compression cycle into a desktop computer and even into a laptop computer. If I package a complete vapor compression cycle in a laptop computer, I need a very tiny, small compressor, as you can imagine, so that favors maybe a fundamentally different concept. Or we're looking maybe at compression concepts that are giving high efficiency at very low manufacturing cost. We might have, and I have an example of that later on. So different driving mechanism that still leads to the fact that people, to this day, evaluating all kinds of different compression concepts. So I will give you a couple examples and the outline that I mentioned. One is a positive displacement extension. One is more of a recip. One is more of a rolling piston design. And so just to see where they fit into this map. So, but before I do this, I would like to talk just briefly about modeling of compressor, because it is an important aspect. When you analyze a compressor, you need, first of all, understand it's a very complex machine. People think, oh, it's just a compressor, maybe pumps gas, compresses gas, no problem. Fact is, a lot is going on in a small hermetic machine. We have thermal, we have fluids, we have heat transfer, we have mechanics, linkages, we have a motor inside the shell, right? And we have oil in the shell, so we have actually a fluid mixture, not too easy to handle. The other thing that comes into place is the time. And because we have these fundamentally different concepts, we have valve openings that are in the microsecond range happening per revolutions, and motor currents and other things maybe in the milliseconds. But then we have thermal effects, heat transfer effects that are in the minute or longer, right? So this dynamics of the machine as it goes through the compression process is also a very, very interesting aspect that need to be reflected during the modeling aspect. So this is the type of model that we typically establish for a positive displacement compressor. It's the core is blown up here to the side is our compression process solver. It takes the geometry. It has a submodel for mass flow rate, for the valves, if you do have valves, for heat transfer, potentially for friction, everything is included. And first of all, solves for the compression process. And if it's a normal rotating machine, It solves on 360 degrees rotation. At 360 degrees, you have to end up where you started out at 0 degrees, and that solves first. And that overall compression process is actually packaged in an overall shell energy balance type model, which also includes maybe additional friction models for the bearings, but clearly a motor model and any other energy transfer models that are going on within the shell, and that we iterate on now on a much larger time horizon, because these are more in the larger time scale from what I showed you before, to find a steady state solution for the compressor operating at a certain operational point. So let's talk just very briefly about the compression process model. You usually have a state equation to define the temperature and pressure during the compression process, and that can be derived either from an energy balance or a mass balance or so, and then you can express either the temperature, pressure, or specific volume or density, either two of those as a function of time, or you can convert the time to crank angle, and that's what's shown here. And then you need subroutines to solve these state equations as you go through the compression process as a function of crank angle, and that is the properties, what fluids is there, and I need to determine my thermodynamic properties for the fluid I'm compressing. You need a leakage submodel, which indirectly is also a valve model. Right, so these are combined. You have leakages and you have valve openings, so you have mass flow rate in and out. So for all mass flow rates in and out of the compression chamber, you need a submodel. You need the geometry, of course. You need mathematically described how does the suction volume change over crank angle, how does it become a compression volume, how does it get smaller until you get to the discharge volume. And then you need a heat transfer model to move the heat in and out of the fluid that happens to the cylinder walls or other surfaces that are in contact with the fluid. So in a slightly different format, more graphical, to show you how then the overall model solves at the end is here's a hermetic shell with some temperatures, some inputs that you initially guess, start out the simulation. And then with the compression process solver, you can determine what is the energy, the work that, or power that I need to drive the compression process, how much heat transfer do I have from the cylinder to inside the shell, and also what is my discharge state at the end of the compression. Now I'm adding kind of a shaft model, a frictional model for the bearings and everything, and the losses typically go into the shell as well. And that allows me now to determine how much power does the motor actually have to put into the shaft to ultimately drive my compression process. Then I need a motor model. So now I need to determine, based on the shaft power delivered by the motor, how much electricity does the motor have to pick up. And then with that, I can exercise my overall energy balance for the entire compressor and determine all heat transfer rate and all steady state temperature at steady state operation for the compressor. And once I have this, I can compare that to my initial guesses and then update those guesses and iterate until it solves. These type of models are rather complex. They require some machines that have significant computing power so that they can run on a reasonable amount of time. But they're extremely powerful because now you have a compressor model that allows you to analyze any type of design change within the compressor and gives you directly performance. And it analyzes the trade-offs. The typical trade-off, for example, when I reduce my clearance, right? I reduce leakage, that's positive, but I increase friction, that's a negative. And you'll find for every compressor design, you find a sweet spot where you get the optimum performance. And that's what we're after when we design these compressors. and this type of model will allow you to do exactly that. So with that, let's go and talk a little bit about our first example of a compressor where we applied that type of model. This is a new compressor called a rotating spool compressor. It's actually quite similar to a rotating vane compressor, also a little bit similar to a rolling piston, but not quite, right? We have basically a spool hub, a cylinder if you want to, rotating inside an outside housing. Inside that spool we have a vane that is positioned by a cam through the shaft. And then we have a suction port and a discharge port, of course, depending on the rotation. But in comparison to a rolling piston compressor or the rotating vane compressor, in this case, the entire spool rotates, and so we have end plates that seal the compression process against the housing. Right? So these are, as you see, like an end plate on both sides, which now moves the sealing surface to the surface of the rotating end plate against the housing, and that has some distinct advantages. If you can run the animation, they will show you a little bit of how this compressor is made up. Right? You have the shaft and the cam together with the vane. The vane rotates with the spool, and then that is put into, there you have the spool end plates that also rotate with the spool, and ultimately we put a housing around it with a suction and a discharge port, and you have the spool compressor. So the advantage compared to a rotating vane compressor is that we position the vane at any point. We don't rely on the friction. The vane doesn't slide on the outer housing. So that is an advantage for us. And the sealing of the end plates against the housing is a fundamentally different concept than sealing a rotating disc against a housing. Here we can actually have active seals, labyrinth seals, different seals to do the job, which works quite well for us. So we did, again, we've developed this type of model that I mentioned. You need to identify the leakage paths, which in this case are numerous, and typically in many compressors they're numerous, right? Across the top dead center, for example, across the vane tip, across the vane sides, right, across the spool end plates. And once you have done that, you can also identify the geometry. You need to understand how does the geometry change as a function of crank angle. And we typically validate our models. Validate means you have to have a prototype compressor. You have to conduct experiments. You have to see how accurate is your model against good, solid, accurate experiments. So we put compressors on calorimeters, on test stands to measure mass flow rate and power consumption. Mass flow rate is typically indicated by volumetric efficiency. Power consumption is quite often is by an overall isentropic efficiency. There are other efficiencies that you can use, or you can compare power consumption directly, as done in this case. And once you're satisfied with the accuracy of your model, you may need to tune it a little bit. The parameters to tune in the model are typically the frictional coefficient, has a direct impact on power consumption. Heat transfer has a direct impact on the discharge temperature that you can measure. And the leakage pass gap width, the flow coefficient for the leakage submodels may need to tune this, which has a direct impact on the mass flow rate that you're predicting. So once you're satisfied, you can do, as I meant, parametric studies or optimization studies. Here on the left-hand side, you see, for example, the volumetric efficiency as a function of the spool seal gap, like how close are the end plates rotating against the housing. You see that if you tighten it up, if you reduce the gap, volumetric efficiency goes up. You can achieve over 90%. That's a very good result. But at the same time, the discharge temperature goes up, as shown on the right-hand plot. And again, you get all of this because of the heat transfers included in one model. And you see that you may have problems with that temperature, with lubrication with oil breaking down at very high temperatures. So in this case, you may need to start looking at how to cool the machine. You could add additional oil. You run at a higher oil flow rate. For example, that would be an easy measure, but then need to separate the oil out after the compression process to handle all this. So just to give you an idea with respect to where this machine is today, we have published this at the Purdue compressor conferences, which again coming up this summer. I invite everyone to come out and see us there if you're interested. But we have achieved with this machine efficiencies that are quite comparable to commercial products, and we are in the process of commercializing this machines through a small business that I'm involved with in Atlanta. That's the first example I wanted to show you. What was the driving factor actually for this type of novel compressor? We feel we can get two efficiencies that are better than a rolling piston, almost as good as a scroll, but with a significant cost advantage. We can manufacture this compressor at much lower cost than what you would do for a scroll compressor. And so we'll see if that all turns out. Let's talk about another compressor, SRAM compressor, that I'm involved with right now. This is SRAM, stands for the Sanderson Rocker Arm Motion. This is an axial machine. It's very similar to some extent to a swash plate or wobble plate type compressor, but it doesn't use the typical mechanism where the piston shoe slides on the plate. Right, in a typical swash plate compressor, the piston shoe slides on the plane, has significant frictional losses, and typically swash plate, wobble plate compressor do not achieve high energy efficiencies for that reason because of high frictional losses. Here we have a mechanical linkage system that is hidden, but there are some patents out there if you want to take a look at it. That significantly reduces the frictional component for this machine and allows us to achieve higher efficiencies. The other aspect of this machine, which is very interesting to us, the pistons move extremely linear inside this machine. And if you know a little bit about linear motion or linear compressors, linear movement of a piston inside a cylinder, you can make the cylinder rather long with a very small clearance, and that allows you to run oil-free. So we specifically use this machine for CO2 compression. Piston cylinder is a very good machine for CO2 compression, and we're running it oil-free, even at the high CO2 pressures, with very good results. So that's the idea. Here, it's a little bit more costly machine. The linkages and the manufacturing is a little bit more costly, so the applications maybe not small scale, but larger scale CO2 heat pumps or air conditioners for various applications. We have a prototype machine that is shown here at the bottom that we tested at the labs. That one was oriented in a vertical orientation, as I mentioned. It's all free, and also through the way that the linkage is oriented with the shaft, I can change the capacity of the machine without changing the clearance volume. I basically move the cylinder up or down how far the displacement is, but the top dead center stays constant. I'm moving the bottom dead center, how far I move the piston out. And so I have capacity control in the range of 25 to 100% without changing clearance volume, which means by almost relatively constant efficiency, very good capacity control. Again, another big advantage of this machine, but maybe a little bit more costly. In this case, we have 5 pistons in our prototype, not the 3 piston machine that I showed in the animation. In our prototype, we had 5 pistons. And again, we determined what is the volume change over the rotation, and all 5 are shown here versus another 360 degrees. And then we exercise the model to give us PV diagrams. For example, on this machine, you see some fluctuation on the suction valves and some fluctuations on the discharge valve, which are quite common in such machines. We can do a conventional PV pressure volume diagram, or determine the temperature, the discharge temperature on the right-hand side. And this is for different, with CO2 for different operating conditions. Same suction pressure, but different discharge pressures, so you can see the impact there on performance. We analyze the valves in detail, just to give you an idea what the model, how accurate it can be on valve, and you see for different discharge pressures how the valve changes.
They're asking a little bit slower because translation has a problem.
Okay. All right. I'm talking too fast, I'm told. I will try to be a little bit slower.
Not much, because then you will need 2 hours.
Yeah, exactly. See, I want to go through a lot of slides, and so then I'm still standing here in an hour. No, I'm just kidding. But anyway, here we determined an overall isentropic efficiency that I mentioned. It's defined typically as the isentropic compression process over the electric power input. Right? So we're taking everything into account. And in this case, we achieved like a maximum efficiency of 70% with our machine, which for a CO2 reciprocating type design, all free, is for us a great result. We're very satisfied with that. And again, development on this machine moves forward. We are in a 2nd generation prototype that we hopefully will be able to test fairly soon. So I think I mentioned most of the aspects of this machine. And let me move on and talk about the linear compressor for a second. So a linear compressor is now a slightly different machine, and I put this into the slide, or into the slide deck, because right, the typical positive displacement machine that we model are driven by a crankshaft. If you have a crankshaft, you relate everything to the crank angle, to 360 degrees rotation. You can't do this with a linear compressor. In a linear compressor, I have a dynamic equilibrium between the gas that I'm compressing, the motor or linear driver that drives the shaft back and forth in an electric field, which I'm switching polarity on to move it back and forth. And then I need to anchor that piston so that it doesn't run out of my electric field, and I do that with a spring. And so I have a spring force, a motor force, and the gas force interacting. And the distance that the piston travels depends now on the power that I put into my driver to activate this system. So my model looks slightly different now. Right? First of all, I have here some inertia that I need to characterize on so I've developed kind of a momentum balance. And then I have some damping forces. I have the spring stiffness. And I need to couple these mechanically. And then in this case, we're running this at resonance frequency. So of my dynamic system that I established, I can determine what is the resonant frequency, and that's where I like to run it. So it looks a little bit different. But once I have this updated model, I can do again what I've done before. I do parametric studies, and here I can determine what is the impact of the dead volume, right, as a function of different friction factors, how the piston, it's an all-free machine as well, because of the linear motion of the piston. I run all-free, it makes my life a little bit easier, but now I need to consider the frictional aspects, and I can vary that and see, depending on the materials I use, the interfaces, and can see what is the impact. So on the left-hand side is the volumetric efficiency as a function of the dead volume. What means dead volume now? I can actually, I'm actively controlling how far I move my piston based on the force that I put into the linear motor. So I don't have to move the piston all the way out. Right? And it may be a function also of my application of the pressure ratio that I see at that point. And in a typical reciprocating machine that is driven by a crank, if I compress gas and don't push it out, I have a re-expansion, and that's a loss to me. This is not the case in a linear compressor. Because if I compress the gas, don't push it out, it comes back in form of the spring force. I can recover it inside the spring, and to a certain extent, not 100%, but some, and that's shown on the right-hand side. Right? I can have a larger clearance volume, don't move the piston all the way up to the end, but I maintain relatively high overall isentropic efficiencies for quite a range of clearance volume, meaning I have a means of capacity control. Right? I'm moving the piston as far as I like to push out as much flow as I like, and even though I'm compressing the gas, I put energy into the gas, it comes back in form of the spring and I'm not losing as much. So it's a very nice means of doing capacity control variable flow rate up to a certain range to about 50% of the flow. Once you get really below that, then it will drop off. All right, so here is for an application of electronics cooling. This is a linear compressor inside a desktop computer. We see the COP of the system in a range from 600 watts to 400 watts. I maintain a relatively even COP, and only when I get down below 300 watts, like below 50% of my cooling capacity, will the efficiency eventually start to drop off. So a very interesting result. This is a comparison to a recip that I already mentioned, an overall isentropic efficiency that we achieved with our machine for a comparable reciprocating compressor. If I would have a larger clearance volume there and don't push out the gas, the efficiency drops relatively linearly. Here, I have much more variation to move this forward. This is our final design of the linear compressor that was proposed to be used in a desktop computer for electronic chip cooling. Application is about 400 watts. It's a gaming application where you have two high-power 200-watt electronic chips on a motherboard to play games, high-resolution graphics, and people like IBM, Apple also are interested in packaging and a whole vapor compression system inside that computer. So this will work extremely well with an overall isentropic efficiency. Again, that is estimated, but should be above 80% at the end if this would go into production. So let's see how I'm doing on time. I think I still have a few minutes, right? Yeah. So I can talk about yet another compressor that we analyzed. This is a bow tie compressor. This is based on a concept by a colleague of mine, Gordon Pennock, who looked at this more in form of a power machine, like more of a power engine type machine, but you can use it as a compressor just as well. You have a rotating, let me see if I can do this, right? You have a rotating crank, and you have a rod connected to this, and as you imagine, right, this rod will now swivel back and forth, and as this swivels back and forth based on the linkage to the crank, right, this mechanism will swivel back and forth, and you're creating a volume that gets smaller and gets larger, so you have a compression process. And inside this compression process, we're putting a suction valve and a discharge valve to let gas in and out, and then the whole assembly is actually spring-loaded, and I will show you why. If I can move the outside cylinder on this machine, I have means of capacity control. Right? So for the same crank and rod position here, I'm moving the outside cylinder from this location to this location, a little bit to the left, and you see that this volume actually changes. I have the same clearance volume again. I can achieve almost the same efficiency, but have means of capacity control. The capacity control in this case is again in the order of 50 to 100%. Not much smaller than 50, but I can do this up to 50%. We built a prototype. It looks a little bit different than the original schematic, where we put a vane here that swivels back and forth through the rod, and we identified leakage passes, just like we did with the other compressors, to exercise our model. We built a prototype and tested it so that we can do a validation of our experiments. And here you see a comparison of mass flow rate measured and predicted, and power consumption measured and predicted. We were quite satisfied with this, and afterwards we can do, again, an optimization. Here on the left-hand side, you see overall compressor efficiency, again, energy efficiency as a function of clearance, and you see, again, the optimum. On this side, leakage losses dominate. On this side, friction dominates, and we know to what clearance we need to manufacture. The other optimization we did is we can make the vane relatively narrow and tall, or long and not so tall. And for either one, we're changing the leakage passes, and that has an impact on performance. And you get an optimum there as well for a certain ratio of the radius of the vane to the height of the vane that's indicated here. So finally, the result of all of this is that with this machine, we were able to design at the design point, which was, by the way, for the refrigerator freezer application. To avoid cycling, we wanted to have capacity control. And in this case, we, at the design point, about 60% overall energy efficiency. It's quite typical for a refrigerator freezer. 50% capacity control. Right? We went down in mass flow rate to 48%, very good result. But the efficiency still dropped a little bit. We went from 60% to about 50%. We didn't completely understand why initially. We thought we should be able to hold it at 60% for the entire capacity range. As it turned out, right, I'm a mechanical engineer. I didn't look too closely at my motor. Not an electrical engineer yet. Still working on that. But with the motor, this was our design point. Right, and as we went to the left, we dropped off in motor efficiency curve, and that is almost the entire 10% that we lost here in efficiency. If we would have a motor that at design point runs here and uses a plateau, right, where we can keep the motor efficiency almost constant, then we could have kept our efficiency almost constant. So in a future design, obviously take a different motor. Very interesting compressor concept, we feel has some potential for capacity modulation but has not been used yet in a real application. So we'll see. And finally, last compressor I will show you for today is the Z compressor. Z compressor is a rotating compressor. So you have a shaft that rotates, and then you put a blade that is fixed along the shaft, and then you put a housing around it, a top plate and a bottom plate, and then a side housing. And so now as you rotate this mechanism with the shaft, you have volumes, and you still need one aspect, and that is the vane shown here in yellow that seals, that is spring-loaded from the top and the bottom and seals against the blade. And now you create a suction, compression, and discharge volumes as the blade rotates 360 degrees. Here too, we developed a simulation model. We need to identify leakage paths. They are across the blade from the top to bottom, on the side of the blade, right, across the vane, up the veins, so various forms that always becomes important. And we did have a prototype. We tested the prototype. We measured a mass flow rate, power input, discharge temperature. We compared it to our simulation model. We tuned the model until we feel we are satisfied with the accuracy to do our parametric studies. With that, we can start doing some type of analysis. We wanted to do optimization of this machine. Shown here is we're changing the height to diameter ratio of the blade by keeping the suction volume constant to deliver the same mass flow rate. By the way, the application in this case was R410A residential air conditioning for mini split or variable refrigerant flow type systems. And you can see here that while some leakage losses reduced, other leakage losses increased. There was no real optimum to be determined based on this geometry change of making a larger blade and more pancake design, or a smaller blade and a more cylinder design. That was not very satisfying. We identified where most of the losses of this machine were, and by far most of the losses were in the blade cylinder contact, the blade running in the cylinder. We need to tighten the cylinder to avoid leakage, and that increased our frictional component and our power loss. Finally, we looked at what is the best overall efficiency as a function of the clearance between the blade and the cylinder, and we ended up with a value of just a little bit over 60%, maybe 61%. That is not good enough for a residential R410 air conditioning type compressor. You really need to be more at the 65 range. And so in the next step, you need, when you get into this situation where simple geometry optimization doesn't get you the efficiency you want, you need to do something else. So in this case, you would have to coat the blade, maybe with Teflon or something else, to get to the performance that you need. At that point, the manufacturer said that is too costly, right? In mass production, when I crank out millions of these a year, I don't want to put a coating to get to the efficiency. So it went back into the drawer where it came out of. It was a nice study, but at this point it was not commercialized. The real advantage of this machine, if you look at the compression process, it's by far the quietest compressor we ever tested at the lab. It's an extremely well-balanced compressor that has very, very low vibration and therefore very, very low noise generation. And so for a market where the noise is dominant, it's a really, really good design. But again, to get to the efficiency with this machine, you just need that little bit of extra. So with that, I'm at the end of my presentation. Again, thank you very much for giving me the opportunity, and be happy to answer any questions that you may have about some of these compression concepts that I proposed to you. Thank you.
Thank you very much. You saved us 4 minutes, so we can allow one question. Please, if somebody has a question, just use this opportunity. If not, then you will drink your coffee with Professor and discuss separately. Thank you, Mr. Groll. It was a pleasure to be with you and to hear your presentation. But we have something what I forgot. It's like a trophy, you know, when we were young.
Yes.
We were getting the trophies for Paris.
Okay, thank you very much. Thank you. Thank you.
Now we have a pleasure to listen to another second speaker today. It's Professor Michael Ohadi. It's also a long CV, what I have to make shorter, but it's very good to see, and I'm always happy when I see so rich biography. Professor Ohadi is Professor of Mechanical Engineering, co-founder of the Center of Environment Energy Engineering, and director of the Smart and Small Thermal System Laboratory at University of Maryland. I think you are working with many of my former students, and I heard from them a lot of compliments about your work. He is a member and past chairman of the Associate Society of Mechanical Engineers in the United States. He is member of the and past chairman of Process Industry Division at ASME, member of ASHRAE, and I think we know each other from these activities, and was in several technical committees, what is the basis of the activity of the ASHRAE. I have some more important things to mention, even that will be a little bit longer than I thought. You have 8 issued US patent, but do you say patent or patent? I never know in America. Patent. And I congratulate for that. I know that that's not easy. You had a lot, and I congratulate to you also. You had 45 master theses and 23 PhD students, and they graduate under your supervision. Again, congratulate to you. That's what I respect as a professor. Somebody is not allowing me to tell you everything about you. And during the year 2002 and 2010, you were assigned as a professional leave from University of Maryland to assist very important organization, the Petroleum Institute, where you served as the founding director of Mechanical Engineering Department. I congratulate for the so rich CV, and I am really expecting something special to see and hear from you. Please, the floor is yours.
Fair enough, Professor Todorovic. Thank you for your introduction. I hope most of you relate to what a data center is. In case you forgot, anytime you pick up your cell phone, you are using at least 2 data centers. So I hope you agree that the number of cell phones is increasing, so the data centers are increasing accordingly. What I would like to do on this 35 plus 10, I'm hoping you will have some questions at the end if I leave time for you, is to briefly, for those of you who are not familiar how we measure data centers' performance, introduce the metrics for a data center, then introduce a case study to see how easy it is to save energy in data centers, and then after that, briefly mention the opportunities for emerging technologies. I did not show the book that, thank you, the book that we have published with a couple of colleagues in this area. We frequently lecture at ASHRAE, and ASHRAE has a very strict policy on commercialization, so I did not want to advertise for the book here, but you're welcome to read on your own what we do not cover today. Right. Okay. All right. So I come from University of Maryland, just about 9 miles outside of the White House. So yes, when we miss the president, we can go in there in about 20 minutes ride. So if you come to Washington area, you're welcome to come and see our labs. I think the building that is shown here, right? It's our laboratory, so we are involved in energy and environmental engineering. Electronic cooling is one of the fields that I work, and data centers, of course, being part of that work. Professor Rademacher and myself, about 20 years ago, we formed the Center for Environmental Energy Engineering. We have more than 35 companies that are part of this center, and of course, many good graduate students help us. What I present here today also is the effort of graduate students We are just coaches, and the real work is done by graduate students and research scientists. So going to data centers, it used to be that we would take the servers and house them in a closet or in a big room, but the modern data centers have realized that just like the electronics being sophisticated and smart, the building that you house data centers also have to be smart. We'll look into how we could measure the performance of data centers and how you could basically save energy in different ways. A typical data center is shown here. As you can see, we have a range of servers that are located here, and then you have a computer room air conditioning that provides the chilled air, but then this chilled air would have to be using some chilled water, and the chilled water uses cooling towers. And cooling towers are gradually being phased out in the US in many of the states because of the water situation that we have. This afternoon I have a presentation on next generation heat exchangers for dry cooling. Keep in mind that the water that these towers consume is among the costs of a data center. You will say energy is cheap these days, and I'll respond to that. First of all, it would not remain cheap. The oil under the ground did not change overnight. Projections are in year 2050, 2030. In both cases, more than 80% of the energy would still come from fossil fuels. And the youngest oil in Middle East is 65 million years old. So it is not something that we could produce overnight. So energy prices would have to go back up again. It's a logistic geopolitical situation that we do have oil cheap now. But even if the oil and coal were to be cheap, there are two factors that would not let energy prices stay low. Number one is the pollution that you produce. And the climate changes are already showing up, but let's have a few more storms, let's have a few uncommon summers and uncommon winters, then the legislators would start looking into this. The Paris conference a couple of months ago came out with very good regulations into reducing the CO2 emissions and so forth, so I do not think the energy prices will stay low. Number two, keep in mind is the water for energy, the amount of water that you consume to produce energy. And I think I have a slide that briefly shows that. So today, the amount of water that we use for power generation is equal to the amount of water that we use for agriculture. And that's phenomenal, right? So if you have a 1,000 megawatt power plant, based on the efficiency definition, that power plant is using more than 2 megawatts of waste heat. So used to be in the past, if I have the slides here, I don't. I think this afternoon I will discuss it more. It used to be in 1970s, we were using rivers and lakes and oceans to do the cooling. Then environmentalists came and said, look, the fish do not like that. Let's not use the rivers. We only allow you to raise the temperature 3 degrees C or so. And as a result, we had to go to cooling towers. The result of cooling towers is now today you're consuming so much water that's equivalent to the agricultural use. Again, this afternoon I'll show you there are many red spots throughout the world, including not in Turkey perhaps, but in US, in China, in Middle East. And so water issue is pretty important. All right, so part two is how do we look at the efficiency of a data center? So what is a data center? Is a whole bunch of servers in a room as large as this. Who are the main drivers, the main owners of data centers, the main managers? IBM, Google, Microsoft, Facebook, Twitter. The first three are the ones that actually would manage your data centers and so forth. So if I go back to a data center and I look at it, I would have a situation like this. So you bring the power to the data center through uninterruptible power supplies. Then you pass them through PDUs, power distribution units, basically get any bad frequencies out of the power so that you are having a regulated power into the servers, and then the servers produce a lot of heat. Now what you have to do is to use a source of cooling to keep this computer cool. Again, on the subject of electronic cooling, we show that for every 10 degrees that you reduce the operation temperature of electronics, you increase the life of electronics by so much, you increase the reliability of the electronics by so much. So temperature, thermal management of electronics is quite important. In fact, within the human body, as you know, our temperatures, body temperatures from person to person can change, but in a given person throughout the day, your temperature cannot vary more than half a degree, okay? So typical human body temperature, 97 to 99 degrees Fahrenheit, but again, temperature fluctuation within the body of a given person only half a degree. So electronics, likewise, do not like temperature fluctuations, and so they need a good environment for cooling. So if you look at the data center like this, how would you evaluate the goodness of this data center? How would you define the efficiency? Okay. One of the most common ways is to say how much power you are bringing to the data center as a whole, and how much of that power is going to the electronics for cooling, right? Comparison of the total power that came to the data center versus how much was used for cooling, that shows how good of a job you are doing in terms of energy management of the data center. Okay, so we call that power utilization efficiency. As you can see here, power to the data center over power to IT. So a perfect data center would have PUE equal to 1, right? So you want to bring the total power that you bring to the data center, spend it all on IT devices, and do not use anything for cooling. That would be great. If somebody shows you a PUE of exactly equal to 1, you jump to say, look, there are certain things we can violate, but second law of thermodynamics cannot be violated. So we will never have a situation where PUE is equal to 1. But we could get close to 1, and I'll show you some numbers as such. All right, so this is showing one typical example of how we calculate the PUE. As you can see here, we are measuring the total power that is coming to the data center, adding up, divide by the amount of power that goes into the IT devices. So if you're having a PUE of 2.72, that means you're consuming potentially 3 times more power than ideal situation, okay? And because data centers are 724, 365, any little change that you can make would make a big difference to the bottom line of the company that are running these data centers, because there's no other expenses. Labor is minimum, other costs are minimum, but there are studies, and we have listed in the book that we have done, that cost of cooling surpasses the cost of IT in more than 3 years, in about 3 years. So if you're not careful with your cooling, you might as well change your servers after 3 years, because technology has changed it, and you will be saving money in that way. So I'm listing here, EPA did a study in terms of the PUE of data centers. As you can look in there, the average in the US is 1.91, and then you have some values that are listed there. Intel, another Intel, German company, Google, National Center for Atmospheric Research, and so forth. The problem is you do not see publication on the data centers that are not doing so well. And what I'll show today is an example of a data center that is called a mission critical facility in our campus, and then you'll find out what the PUE is standing in there. More details, graph we are showing you up there in terms of how the PUE across the country sits. So as you can see, most of the data centers are here. So if you see what I showed you, they're really on the minorities. So to the left side, between 1.01 and 1.25, there are very small number of data centers. And anytime you go close to 1.1, 1.2, you are not really using chillers. You are going to Montana, or you're going to Norway, or you're going to Denmark, and you're using free air cooling to achieve that PUE. The moment you use chillers, then your PUE is close to the average that we showed. All right, so I'll show you one chart that SIA projected. This is Society of Semiconductors, projected in 2003 that by 2015, air cooling will no longer be sufficient and we have to use liquid cooling. But today we know that that has not happened. We do have some liquid cooling, but still air cooling is doing it. What I would also propose to you is that there is a lot of room for energy savings. You really do not need to go to liquid cooling yet. And this example will show you how easy it is to save energy in a given data center. Okay? All right, so what you're looking in here is distribution of servers sitting in a room like this. This is data center. What problem do you see immediately by looking at this chart? It is a room that is not fully utilized. There's a lot of empty spots, and that's right here. And this should really be blocked out, and otherwise you do not keep this center cool without any servers in it. Okay? So the density of electronics is listed here. You have numbers that are ranging from 2,000 watts all the way to about 20,000 watts or so, and so different densities throughout the data centers. The good news is that we have experimentally measured and tested against, I don't want to mention the commercial software name, but there are a number of them. These softwares can give you numbers that are within 10% of the measurements. So you could really use softwares today to design your data centers very effectively, such as what? How to place these servers, how to project CFD, flow of air through these centers, and what if you change this, what if you change that. So this is the greatest news in terms of designing a data center and the progress that has been on the software side. Okay, so I'm looking at typical savings in ECM's energy conservation opportunities or measures. And then you will agree with me that there is a lot that one can save in a typical data center. So what we found in this data center after we ran the model was that there are some cracks, computer room air conditioning units that you saw in here. As you can see here, there are 8 cracks in this room, one here, one here, one here, there. So placements of these computer room air conditioning devices should be properly oriented so that they are complementing each other and they're not really fighting with each other in terms of airflow distribution. Okay, so if you look at this graph here, we found out that if we turn off these 2 cracks, we actually improve the operation of data centers. So we have too many cracks in this room, and we could turn off 2 of them based on the CFD model that you can see here. So red is not good, blue is good, and the color coding is up there. So by turning 2 of these cracks, we actually identified by turning 3 cracks off, But the facilities management, the IT people said that we want to have that other crack working just in case one of them fails. And there is redundancy in data centers, so we said it's fine. But otherwise, 2 for sure. And this work was successful because we had total support of the facilities management, and they worked with us. We showed them models, we showed them measurements. We said, go ahead, we guarantee that this would help your data center. And they did actually turn this to cracks. And I'll show you the savings that came as a result. But as you can compare the upper figure with the lower figure, you can see that a lot of hot areas were removed. This yellow area became less yellow, which means it's cooler, and all in all, win-win, no matter how you look at it. Okay, so air distribution in data center is prime concern to be watched for. And then, as I said, I'm not showing a lot of data here. We have written papers on this, and they're documented. You're welcome to look at it. But we started measuring data and monitoring the servers because this was a mission-critical facilities. Student records, financials, all private information of people, 37,000 students and so forth was in the data center. We were very careful not to do something that we can lose data or have any sort of failure. So as you can see here, as a result of turning off, we substantially dropped the temperature in the data center, and it's showing you the dates that we do that measurement. ECM number 2, increase crack set point temperatures. So those of you who keep up with ASHRAE TC 9.9 mission critical facilities, that committee has 100 members. Just about all the electronic companies are involved. And what they have done very nicely in recent years is, used to be this red envelope is what people were running data centers at. But actually through the past 10 years, and many publications and many research has shown that you can actually operate in any of these envelopes. Again, we discuss this in details in the book if you want to know more, if you're not familiar with. But areas in Europe, they're operating in A4. I have one of my sons works for a commercial insurance company, and one of the things they do anytime you change your envelope or you change the cooling type that you're using in your data centers, the insurance company sits down and start looking at your policy to see if you're taking any higher risk. And they increase your premiums if you are really going into something that could be riskier. But what the manufacturers are saying is they would warranty without question if you stayed within this envelope. If you went to any other envelopes in here, they would still hold their warranties for the most part. You have to check your policies. They would hold their warranties so long as you change your servers in 4 years. So they will give you 4 years. However, at the rate that technology is changing, you are better off changing your servers in 4 years, right? The cost of cooling exceeds the amount of money that you would have to spend to change your servers. Okay, so we decided to increase our set point temperatures, and I think on this chart, it would, let me see, right here. So in this chart, we said we used to be running at 16 degrees C, pretty cold because a typical computer chip can run 80 degrees C. So we said let's have the minimum temperature to be 11 degrees C, and the maximum temperature that goes to the servers be 32 degrees C. Still, as you can see, we are pretty conservative in this area here. We are still pretty conservative. We are not really going to the extremes of any of these envelopes. So if we did that, I'll show you in a bit what the savings with that would be. Then we looked at an ECM number 3, and that was separate the hot and cold aisles so that the cold and the hot air don't mix up with each other, and you have a situation that you have complete control over the airflow rate. So all you have to do, and this is a pretty inexpensive solution, all you have to do is to separate the chilled air that is going to the servers, and then the hot air that comes out so that you can return it back to the room air conditioning unit. All right, so schematically shown here. And then the software would show you if you did that, you substantially improve your temperatures. We found out for this data center, the cost was $3,000. The annual savings is $15,000. Therefore, the payback is like in 3 months. So separation of hot and cold oils is one of the easiest things you can do and quick savings. As you can see here, 3 to 6 months payback period. How about variable speed drives? The technology is improving, so as the demand, as the outside air temperature gets cooler, you could reduce the speed of the crank, the fan that is circulating the air to the data centers. So we know that if you double the RPM of the pump, what would be the new power consumption? The power consumption of the fan goes up by 8 times. Right? So if you double the RPM of a pump, you increase the power consumption by 8 times. Likewise, if you half the speed that a fan is working, then power consumption comes down 8 times. So speed of the fan could be something that could be easily controlled. However, for this data center, if we did that, the cost versus the saving, as you can see, would take us 3.6 years to pay back for it. And in our campus, the magic number that people will go for any energy efficiency is about 5 years, and they don't want to look at anything that is more than 5 years payback period. So 3 to 5 years is basically a good number. ECM number 5 is fresh air cooling. Again, this thing, many work has been done, including work in our group, to find out how you could use fresh air cooling in terms of shutting the chillers down and using outside air to cool your servers. Right? So people have questioned the problem with humidity. ASHRAE conducted a research project recently and found out you could actually vary humidity greatly, from as low as a few percent to as high as 90%, and your electronics would be safe. This is a very new finding, probably a year old. I go regularly to TC 9.9, and there are publications from ASHRAE that you could look up. So with that, fresh air cooling is becoming more and more attractive. So the only time that you have to be careful with fresh air cooling is when you have downtown Beijing or downtown, I'm not sure how polluted the air is in Istanbul, but if you are operating in a very polluted environment, the acidic stuff that you bring in with the pollution to the data center, they could cause damage to the servers. Your insurance company would not like it. Your policy premiums will go up immediately. Other than that, if you are in suburbs, if you are in places where the air is free of pollution, then you can just filter with regular filters and get the dust out, and you'll be fine. So fresh air cooling naturally would give you the highest saving. And again, you could read about this. There is an economizer that automatically decides what % of free air comes in, what % gets recirculated, automatically would do all of that for you as such. So we are looking here for Maryland, and as you can see, I can operate within the envelopes that I showed you, A1, A2, A3, A4. So A1 was the most conservative, then A2, as you remember, A3, A4. If I operated in A2, 86% of the time, the weather in Maryland would satisfy data center based on ASHRAE envelopes. And Maryland goes through complete 4 seasons. We do have a bad summer, very hot, very humid, so don't come to us July and August. Pretty hot, pretty humid. We have fall, we have winter, and we have spring. So this data center, 86% of the time can use fresh air cooling. Why not? And I'm not saying if I go to A4, 97% of the time I can use fresh air or outside air for cooling, therefore pretty attractive to begin with. All right, and this is computer software showing if I use fresh air, I get pretty nice temperatures. You don't have any hot spots as such. And the reason you do see some hot spots might be the 13% of the time or so that the fresh air cooling is not proper. In that case, you can have 1 or 2 cracks in the data center that would sit close to the hot spots and cool up. So if I were to summarize for you this one small data center on an academic campus that claims to be well run, we spend the facilities management at University of Maryland hires 870 people. So it is a pretty big operation. For a small data center, as you can see in here, each of the ECMs are listed. ECM number 1, just turn off a couple of cracks and you get $10,000 saving. ECM number 2, spend $2,000 to $3,000 separate hot and cold as you get $15,000. ECM number 3, increase the set point temperatures, very conservative in our case because they were very scared that this data center is very important and they don't want to mess around. With most conservative, you still are about 15,000. And then variable speed about 12,000, and then this thing is about 130,000. So you add this up, you get about $200,000 per year from one small data center on board of an academic campus. Okay, so with that, what is the future trends? Well, the future trends are in 2 categories. One is academicians who want to do innovative ideas, and we think that, look, we will shake the earth loose if you use my technique because I like it, but the fellow who's running the data center is looking at how much profit will come out of this. Is it practical? Do I have a need to do it at this point? The example I showed you demonstrate to you that, look, we have plenty of room to go before I have to go to exotic solutions. But let me look at some near-term situation. So the power in the data centers is going to go up and up. That's for sure. Because the number of cell phones, I have separate slides where it shows the increase in China, the increase in India in terms of the number of cell phone users and how the power is projected to increase. But more importantly, we had a panel a couple of years ago and we had people from Intel. They said we are not going to make faster chips anymore because we will not have enough power plants to supply electricity. So what they're doing today, the Morse chart is really reaching a plateau. They are not increasing the speed of the computers the way they used to because they produce too much heat and we do not have good ways of cooling them. So we will increase the power because the number of transactions, the number of cell phone users and so forth, data center will go up, but we would like to keep it such that the power consumption is minimized. Air cooling versus liquid cooling versus phase change cooling. So what this nice graph shows you is if you were to choose air cooling versus liquid cooling, this is how much you can reduce the size of data center. That's very true, right? So we occupy about 20% of space in buildings just to accommodate air. If you go to liquid cooling, you can get rid of that. And IBM has been a big prominent supporter, promoter of liquid cooling, and liquid cooling is finding ways to come to the market, but still many of data centers are bad air cooling. What's this little spot here? Is if you change from liquid cooling to refrigerant cooling, okay? Again, we do have door-cooled data centers today. We have examples of refrigerated cooling systems. IBM, again, is marketing this heavily. But we still have plenty of room to go with air cooling alone. Okay, what else? DARPA sponsored a project, very interesting work, that look, how is the human brain cooled? You have a pool of water. The brain is sitting in a pool of water. It does not like temperature fluctuations. If you have a couple of degrees of fever, you jump to cool And to cure it, particularly when you see the hands and the feet becoming cold, then what the brain is doing is shutting the blood flow to the fingers and to the feet so that the heart and other critical organs are protected. So again, thermal management pretty important, but embedded cooling means, look, why should I have the computer chip here and then a piece of copper attached to it, and then I have thermal paste in between, and this magnificent computer chip that is 1 centimeter square, that has more than 1 billion transistors on it, is such a sophisticated system. It costs $5 to $10 billion to have a macro fabrication facility. Now a dumb piece of copper sits on the back of it simply to diffuse the intensity of heat. So embedded cooling means I go right on the back of the silicon and I put channels to cool the electronics directly. So listen to this. The distance between the source of the heat, and we are one of the performers in this program, and we're getting some really interesting results. The distance between the hot element where the junction is and the temperatures are really close to the temperature of the sun, meaning that where your electronics is, and particularly for radar application and so forth. The intensity of heat is close to what you have in the surface of the sun. Okay, so we all have on this centimeter square about 10,000 channels of cooling. What's the gap between the heated element and the cooling channels? 100 micron, hair thickness, okay? Result, substantial compaction, substantial compaction. So we have an ITERM conference coming up at the end of May in Las Vegas. If anybody wants to come and do some gambling, this is all about thermal management of electronics, and several presentations there will talk about embedded cooling. Immersion cooling. What's immersion cooling is a brain way of cooling. You basically put electronics inside of a pool of liquid. Is it new? It's not. It was done in 1970s and 1980s, was not cost effective, but now people are going back to it. And I blocked, again, practicing X-ray policies, I blocked the name of the company, but these people claim that you could get your monies back in 2 to 3 years. I think it mentions on the slide, because they claim the efficiency is a lot better when you put this electronics inside of the cooling. So you basically have a tank of liquid that you would put this electronics on. You could have many servers, racks inside of this, and you have sensors at different levels in case you do have leakage or you have evaporation and so forth. Any safety issue will be addressed. This graph is showing you that, look, do not count on projections. It really depends on market push and pull, supply and demand. So this projection did not come true as you agree today, right? I think coming close to end of my slides, a good thermal management, a comprehensive thermal management of data center at any organization would not take place until you bring 3 entities together. Overall management, president of university, president of company, upper management of university must, or company, must believe in energy conservation. If they say they do, then the lower ranks will start listening. So you have overall management, they're looking into energy management policies, they're looking into remote monitoring, and they're looking into setting strategies for maintenance management. Then you come to IT people. These are people who are into electronics. They oftentimes have little concern for energy savings, but they want to make sure that the data center operates reliably. Very different thinking than mechanical engineers, than architectural engineers, but we have to communicate with them. So the work that we have been doing with our campus, all these entities are involved. We sit in the same table and we publish papers together, so that I'm not really criticizing our facilities management. We're looking at the problem together, and we are accepting that, look, we are wasting energy big time, and let's do something about it. And tier number 3 is facilities management. These are your technicians who have to go and turn the cracks down, who have to go and change the data sets, set points, and you bring them on board. And if they do understand what you're doing, they will support you, and they would make sure that failure does not happen. But if they do not understand what you're proposing, it really does not work. And none of this really matters. None of this matters if a data center security is being compromised because you want to save energy. No. One incident could put the company out of business. One incident could put the university into big trouble. So that is prime concern number 1. Anything and everything you do, you have to go by standards. You have to go, even within standards, you have to stay conservative, because this is a mission-critical facility. This is not a typical building that you could have a situation where you would have failure of cooling system in a given day, and people will sweat a little bit and done. By the way, the computer models software will project for you catastrophe failure. So you could put in the software, what would happen if I lose all of the power? And the software, the models are improving, but the software will show you most data centers can only survive about a couple of minutes, meaning just enough